Yeah, welcome everyone to our fourth weekly discussion session for the Physics of Nanoscale Devices NPTEL course. I'm Jyotishwaran, a PhD student from the ECE department of IIT Roorkee. So today we shall be covering the topics from week 4 of this course. So the topics that we shall be looking at are the Fermi-Dirac distribution. Essentially, we'll carry on from where we left off last week. We shall be looking at certain properties of the Fermi-Dirac distribution function, and we shall use those properties to define Fermi levels in solids and the effect of doping on the Fermi levels. So here it is understood that this is the effect of doping on the Fermi levels. So, and after that we shall spend our time discussing the ballistic transport model. So this is what is explained in the lectures as the generalized transport model. So here we shall look at how to define the charge density in materials. Essentially, this will give us the stored charge, and then we shall look at the current flowing through the channel, and in that we shall conclude today's session by discussing the notion of modes in a ballistic channel. So if you have seen the week 4 assignment, you will notice that there are no numerical questions in the assignment. So in order to help you better solve the assignment questions, I shall actually be doing a bunch of derivations in today's problem solving session. We'll also be solving 1 or 2 numericals, but primarily our focus will be on the conceptual side of things, so that you also get some help with the assignment questions. So I'm moving on to our first topic. So yeah, the Fermi-Dirac distribution, like previously last week we defined this distribution function as f of e is equal to 1 over 1 plus exponential e minus ef or mu by kBt, where EF is the Fermi energy. So EF is the Fermi level or the Fermi energy, and T is the temperature and Kb is the Boltzmann constant. So this is the distribution function. We saw some properties of this. We essentially discussed where this is applicable and what form or what shape this function will take at different temperature values. So today we shall look at one final property, which is a very important property, that is the symmetry of this function f of e. So if I draw the graph for f of e versus the energy E, then that function will have the following symmetry about, oh, okay, I made a small mistake, it's not Fe, it's Ef. Let me just correct it right here. So yeah, this should be F and this should be yes. So yeah, so as the following symmetry about the Fermi level Ef. So what is said is that f of Ef minus E will be 1 minus f of Ef plus E. So what this means is, if I take the if I just sketch the Fermi distribution function, and let me say this point, this line over here is my EF. So this over here is EF. Oh, I used the wrong pen. Yes. Yeah. If this over here is EF, then at any temperature, at any non-zero temperature, our graph will look something like this. Now the point is, about EF, if I go to some energy value delta E in this direction, the value of f of E will be 1 minus the value of the function if I go delta E in the negative direction. If I go delta E in the positive direction, then whatever value I get will be 1 minus the value of the function if I move the same delta E in the negative direction about EF. So this is the symmetry property of the Fermi distribution function. This symmetry has to be followed at all times. Wherever we consider the Fermi-Dirac distribution, so this point, so essentially if the value is F1 over here and if the value is F2 over here, then F1 is equal to 1 minus F2. And you can see that this expression is essentially symmetric. I can bring F2 here and F1 here and the expression will still remain the same. And from this we can also see that if I set E equal to 0 here, then we will get twice f of EF is equal to 1, which implies f of EF is 1 by 2, irrespective of the temperature. So this is the symmetry property. I will also write that here. It implies twice f of EF is equal to 1, which further implies that f of EF is equal to 1 over 2. This is something we discussed last week. So no matter what the temperature, the value of the Fermi distribution function at the Fermi level is always going to be half. And this quantity EF depends only on the available energy states in a system. So whatever object or system that we are considering, like if we are looking at the solid, it just depends on the energy levels that are available in the solid and the number of particles, electrons or anything else, which I mean any other fermions which we are considering that occupy this system. It does not depend on any other quantity. So it is a property of the system and the number of particles occupying the system. No other parameters are involved in defining EF. Later on, as we move further ahead in the course, we will solve some problems where given a particular system, we will try to define what the Fermi energy is. However, we won't do that today. And as I've been mentioning again and again, the Fermi level is independent of the temperature. It has no dependence on the temperature. So this is the last part of the things that I wanted to cover on the Fermi distribution function. So now let us go to some problems. So now we shall use the symmetry property of the Fermi distribution function to do the following. We shall consider a material whose valence band is completely filled at T equal to 0 Kelvin. Okay, so we are considering a material where I have, say, the valence band like this. So the valence band is completely filled at T equal to 0, which implies the highest unoccupied band, which is the conduction band, is completely empty. So a common example for this is silicon. Silicon has this kind of a property. So for such a material, we now want to sketch the Fermi distribution function for a non-zero temperature. That is our first exercise. So how do we go about doing this? So generally in such problems, what we do is we first sketch the band diagram, so that we define our energy levels. So we have our conduction band and we have our valence band. The curvatures are just representative. These are not the actual curvatures of the band. And this is my energy axis. So I'm going to call this energy EC and this is EV. So this is the band edge energy of the conduction band. So I'll just write here C is the conduction band. And V is the valence band. So this is problem A. So yeah. Now we want to find out how the Fermi distribution function will look for this system. This is our energy axis. So our curve will be plotted in this direction. So this is the increasing axis of energy. So the only thing that we have to figure out is where the Fermi level is. If we figure out where the Fermi level is, then we know how to draw the function, because the form of the Fermi distribution function is known to us. So we only have to locate at which point the Fermi level is. After that, everything becomes straightforward. So how do we find out at what region the Fermi level will lie. So if we were to take the definition that it is the highest energy, like last week I mentioned that it is the highest energy an electron or a fermion can have in the system at T equal to 0 Kelvin. By that definition, the Fermi level should be here. It should be at EV, because EV is completely filled and EC is completely empty at T equal to 0 Kelvin. So do we have the Fermi level at EV or is it at a different point? So to answer that question, we have to use the symmetry property. Essentially, whatever Fermi level we choose, our distribution function should be symmetric about it, which implies whatever curve I draw here, it should have some symmetry about some point between EC and EV. So to arrive at that, what we have to notice is that in a solid, all energy levels are not permitted. The electron can have energy EV, and after that it needs to gain the band gap energy delta E or EC minus EV to go to the conduction band. All the other intermediate energy levels are forbidden in the system. Like it cannot have those energy values, which implies, let me assume that at some finite temperature, the electron which is at the top of the valence band gets excited and goes to the bottom of the conduction band. So, and that is the lowest energy exchange that can happen for an electron to move from here to here. Therefore, the norms essentially at finite temperatures, what happens? We say that the probability of finding the electron greater than EF gradually increases. But the lowest energy greater than EF where I can find an electron in a solid is EC. So let me write this down. Lowest energy level above EV is EC, which implies when an electron gets excited from here, it will go automatically to EC. Therefore, as the probability of finding an electron in this region decreases, the probability of finding an electron in this region will increase. So the symmetry is actually not about EV, but across this line. And because of that, we have to choose our Fermi energy between EC and EV. So this is where EF lies. And so due to this, our function, our Fermi distribution function will be like, this is my axis for f of E. So this is f of E. Okay. So like this is the increasing direction. So it will go like this, and it will, yes, and it will be something like this at a non-zero temperature. So this is how the Fermi distribution function will look for a solid, where I have these properties, like where essentially the valence band is completely filled at T equal to 0 Kelvin. Now, if I had a different kind of filling configuration, then again this Fermi distribution function will look different, which is why I said EF depends on the number of electrons that are present and the available energy level. So that is exactly why I covered these concepts before starting off with this problem. So roughly it is going to look like this, and again about this line the symmetry property will be followed. And so this will automatically, so I will write the value of EF here. So EF for this case will be EC plus EV by 2. And moving on to part B. Part B is a pretty straightforward question. Part B for this is where will the Fermi level lie? So that has been answered. Okay, so yes. So this itself is part B. So we have to move on to part C. Now that the Fermi level has been defined, again changing the temperature will not change the Fermi level. Therefore, at T equal to 0 Kelvin, Now we will be able to draw the correct Fermi distribution function for this system. So again, I have EC, I have EV. So this is EC and EV, and EF this time is going to be right in the middle, and at T equal to 0 Kelvin, so this is T greater than 0, and so over here the Fermi distribution function is going to be flat all the way here, and it will immediately cut off to 0 at this point. So this is EF, and this is F of E. So this is for T equal to 0 Kelvin. The final part is we are asking, will this material behave as a conductor? In general, the answer is no, because the probability of finding an electron in the conduction band, as we can see from this, at any given temperature is significantly lower than finding an electron in the valence band. So in fact, yeah, if I'm being very precise, I should slightly change this graph at not 0. So it should be up until here, and then it should, oh no, it should be something more like, yes, and yeah. So whatever change I am getting here should be present over here. So that is the symmetry property. Like the curve will be a bit smoother. I apologize for any irregularities in the drawing as I'm drawing it by hand. But similar figures are available in the slides. So I hope you get the meaning of it. So part D is answered by saying, in general, such a material is an insulator. So all 4 parts for this question have been answered. Now moving on to the second question. Now we are looking at a similar material as the previous problem, but now it is lightly doped with acceptor atoms. So this system is now doped. So now what will happen to the Fermi distribution function? So again, most of us know what's going to happen in this case because we are familiar with semiconductors and their properties. What I'm trying to do here is to emphasize how just understanding the behavior of the Fermi distribution function will enable us to predict the behavior of this material. So this problem is not to explain to people how a p-doped semiconductor will be able to conduct currents. That is not the aim here. The aim is to show what impact the Fermi distribution function has on this phenomenon, or rather how this phenomenon reflects itself on the Fermi distribution function. So yeah. So first, again, we are supposed to sketch the Fermi distribution function at T equal to 0 Kelvin. But now we have said that this has been lightly doped with acceptor atoms. So what is going to change? Again, I have the conduction band, I have the valence band. So I have EV over here and I have EC over here. However, now what we are supposed to look at before we start drawing our Fermi distribution function is, so this is where I'm going to plot. Now before we do that, what we have to look at is, this is the increasing direction of energy. What happens when energy is supplied to an electron at the valence band? So if the electron in the valence band gets some energy, where is it going to go first? In the previous case, it could either be at EC, EV, and then the next immediate energy value it can possess was EV. That was the lowest energy level above EV. But in this case, that is in the doped case, that is not true, because when we have doped our material, what we have is essentially an acceptor level. So we have the acceptor energy level present in the material. What does this mean? Like if I have an acceptor atom, one of the electrons from my materials atom, like if I'm doping silicon with, say, what would be a p dopant, with yeah, gallium, or I don't think we can dope it with boron. Yeah, gallium is a good dopant. So if you are doping it with gallium, what will happen is gallium is trivalent. It only has 3 electrons in its outermost shell. So one of the electrons from silicon will move over to the gallium orbitals. So that is denoted by this acceptor level, which implies an electron that goes from here need not go all the way to EC. It can rather go to the acceptor level, which I shall call EA. So there is an acceptor energy level, and when an electron gets excited, it will just jump over to the acceptor level. And now what happens to the conduction? What happens to the dynamics of the material? What happens is, in the previous case, when an electron gets excited from the valence band and goes to the conduction band, the electron in the conduction band is free to move, and the vacant state that is created by the electron here, the valence band, is available to all the electrons in the valence band. So that is why in such semiconductors we create what are called electron hole pairs. So we create charge carriers in pairs. There is an electron, and for each electron that is created, a hole is present, created in the found in the conduction band. There is a hole in the valence band. That is true for an intrinsic semiconductor. But here what happens is, when the electron gets excited from the conduction band, it goes into the acceptor level. It is no longer in a free band. It is in fact bound to the acceptor atom. So that electron is no longer going to participate in the charge carrying, in the current conduction process. So the distribution of electron probability is no longer going to be symmetric about this line. It is no longer going to be symmetric about EC plus EV by 2. In fact, if I give this much energy, then a vacancy can be created here. So the new Fermi level will be, can I use a slightly different shade? Yes, I will use this. So the new Fermi level, sorry, the new Fermi distribution function is going to look something like this. It is, oh yeah, this is fine. So it's going to be like, this is flat, it's not increasing, and it will vary from here, and it won't decay so far, it will decay rather quickly, and again it's not crossing over the axis. Oh no. Yes. Yeah. Oh no. Just 1 second, let me just do this once over. Yeah, so it's going to be something like this. So even before the electron gets excited to EC, it is possible to excite it to EA, and then conduction will take place. However, any electron that goes to EA will not participate in the current conduction, like the current carrying process in the material. So now the Fermi level will actually be somewhere between EA and EV. But usually in materials, this acceptor energy level is very close to EV. So EA plus EV by 2 can be taken approximately to be approximately EA. Now this is an approximation, which is why this level is no longer the Fermi level, but We all know this term. In doped materials, this is called the quasi-Fermi level. This kind of behaves like the Fermi level, but this is not the proper Fermi level of the system. To understand the proper Fermi level of the system, we will have to again analyze the whole doped semiconductor system, look at how the energy levels are changed, and then redefine the Fermi level from first principles. However, like we don't do that because it's lightly doped, so the impact on the material is somewhat like we can say that for all intents and purposes, the material by and large remains like the original, like the undoped intrinsic semiconductor, but the introduction of the acceptor only changes the charge carrying dynamics. So in this case, there is an acceptor level and excitation happens to the acceptor level. If you look at week 4's assignment, there will be a question in a very similar spirit. So I hope this will help you solve that. So part A is done. Now part B, we have said that a Fermi level is not technically definable in this case. So Fermi level EF is approximately, not exactly, at EA, and this is the quasi Fermi level. This is not the exact actual Fermi level. This is not the proper Fermi level. And part C. So the nature of the current carriers in such a material. Now that is what I have been explaining. Any electron that goes to EA will not participate in the current carrying process. Therefore, majority. However, at any given temperature, there is a finite probability for the electron to go to EC also. So one should not disregard that. A finite fraction of the electrons will definitely go to EC. So we cannot say that all the charge carriers are holes. Majority of the charge carriers are holes. So this is the understanding of how doping affects the distribution, essentially the Fermi distribution in a solid. So this was the last part that I wanted to cover from week 3. I mean, this is technically part of week 4. And now you can see that most of the calculations that are done in a typical semiconductor devices course, we have essentially understood those concepts more or less graphically. Like we have not done any numericals here. All we did is we considered the symmetry property of this Fermi distribution function and we kept imposing it in every condition that we encountered. If we took an intrinsic semiconductor, we said, okay, the Fermi distribution function should be symmetric about whatever EF I define. Then we look at what are the available energy states, and based on that, we are able to define the Fermi level. So for an intrinsic semiconductor, it is at the midpoint of the conduction and the valence band. For a doped semiconductor, we know that exactly defining the Fermi level is difficult because we actually do not properly define the doped semiconductor system, but it is approximately somewhere close to EA. And due to those cases, we call it the quasi-Fermi level. So with that, we come to the end of the Fermi distribution function part. Now, majority of today's session, we are going to be spending in the transport model, as was the case with the previous weeks. I mean, week 4's lectures, most of the lectures were spent on the ballistic transport model. So what we shall essentially be doing is, again, no numericals were done during the lectures and no numerical questions are present in the assignment. So what I will do is, in a rather quick manner, I will walk through the derivations of these expressions and the considerations that go into them. So in a ballistic transport model, the stored charge density in the channel. So essentially, what do we mean when we say ballistic transport model? We have a source and a drain, and we have a channel in between. So this is my source. But right now we need not think about them as source or drain. We will call this material 1, this is material 2. They may be the same material, they may not be the same material, and then we have a channel. Now what we are going to see here is this channel is no longer. So yeah, let me start listing the assumptions. So first assumption is 1 and 2 are not or, it's R. So regions 1 and 2 are bulk materials. So they are considered to be macroscopic. So they, for all intents and purposes, we will consider these two to be essentially 3D objects. Okay. And the number of atoms present here and here is much larger than the atoms present here. So the channel is small compared to this diagram does not reflect it. Here the channel looks longer than the contacts, but what is to be understood is that, so this is the first assumption, and the second assumption is channel is very small. In fact, if we go all the way to quantum dots, then the channel is point sized for all intents and purposes. So small compared to the contacts. So for now I am not calling these source and drains, I am going to call them contacts. Okay, so contacts 1 and contact 2. So now we are going to study the conduction of electrons in such a system where we have two bulk contacts and a channel which is very small. So these channels in general are referred to as of course this is a ballistic channel, but in terms of their length, these fall under what is called the mesoscopic category. So these are mesoscopic channels. So what does mesoscopic mean? Mesoscopic is like it is like sub-microscopic. It is smaller than a microscopic object. So the length of this channel here is not to the order of micrometers, it is of the order of nanometers. So it is much smaller than a microscopic channel. So yeah. So this is a mesoscopic channel and length is of the order of nanometers. So maybe few nanometers or tens of nanometers, or I mean not even tens of nanometers, it is usually 10 to 15 nanometers or less than that. And I mean these days we are trying to push into the sub-nanometer regime. So that is what the state of the art is. However, to understand that we need to understand how mesoscopic channels behave. So the current expression is given by, so here again I'll have to clarify here. So D of E is the density of states, and F1 and F2 are the Fermi functions of contact 1 and contact 2. So the charge density that is stored in the channel is given by D of E by 2 into F1 of E plus F2 of E d. It's an integral. And the current flowing through the channel is given by this quantity here, 2q upon, and q is the charge unit. We are not using small e because sometimes we take exponentials, so there we use e. So in order to avoid any redundancies, we are using q for the charge. So this is again approximately 1.6 into 10 to the power minus 19 coulomb. So this is the fundamental charge. So 2q by h is the Planck constant. Again, integral gamma of E pi d by 2 F1 of E minus F2 of E integrated over all available values of energy. Now this gamma of V is what is called, gamma of E is what is called the energy broadening in the channel. Now this is a quantum mechanical effect because we have now moved to a regime where quantum mechanical effects are prevalent. If you go back to week 1's video, I mentioned the case where as we go smaller and smaller and smaller, the quantum effects become more and more and more prevalent. So this is one such case. So this quantity gamma E is the quantum mechanical effect. So this is a quantum mechanical effect. I'm just writing it. So all the quantum mechanical effects in the channel come from gamma E only. This D of E times F of E is something we actually do to estimate charge densities in bulk semiconductors also. So people who have done like introduction to electronics as semiconductor devices or things like that would be familiar with integrals of this form, where we do D of E into F of E dE. But this gamma parameter is new because now we are considering short channels, like very short channels. And this energy broadening depends on the transit time of the electron. Essentially, it depends on the time an electron spends in this channel. So an electron with certain energy E, let us say it spends a time tau. So this quantity tau is a function of E. Then tau of E is related to gamma of E by this quantity, h bar by tau of E. And this is due to the Heisenberg uncertainty principle. And this is why we also like did some problems based on this principle way back in like week 1, like 3 weeks ago. So this is from Heisenberg uncertainty principle. So this is the energy time uncertainty principle, which essentially says delta E times delta T is of the order of h bar. Like people say h bar by 2, but it's comparable to h bar. That is the understanding here. So otherwise, people will say it is greater than or equal to h bar by 2, but we don't go into that specific form. This is what we want, and because of that, we define the energy broadening as this. Again, this is not the exact quantum mechanical effect. This kind of reflects what happens due to the short channel. We will see pretty soon what implication this particular effect will have. Okay. So problem 3, this is going to be the longest problem in today's session. We shall quickly go through, not quickly, like take as much time as required to go through the derivation of the expression for the stored charge density and the current flowing through the ballistic channel. And finally, we also have to answer the question of what will be the Fermi energy or Fermi level at equilibrium for such a system. So to do this, we'll have to consider, the reason I'm doing this problem is, in this derivation lies the answer to most, if not all, of the assignment questions. So I'm not doing this just for the sake of solving a problem. Please pay attention to this so that you can, figure out the necessary answers, the answers to the corresponding assignment questions. So first, what I'm going to, now this is not a material diagram, this is a like energy diagram. So we have yes, so this is region 1, this is region 1, and the axis here is energy. Okay, so the red zone indicates the presence of electrons. So this is EF1. So this is the Fermi level of contact number 1. So what will happen in general? And this is my channel. So this is the channel. Let me just use a different color just to maintain clarity. So this is the channel. So essentially what I'm trying to tell is, whatever electrons here, since these are bulk materials for all intents and purposes, we will assume that there are infinitely many electrons here. The number of electrons present here is significantly larger than any number of electrons that can be present here. Even if this channel, apologies, even if all the energy levels available in the channel were populated fully, the number of electrons present here will not even compare to the number of electrons present in either contact 1 or contact 2. So that is what we mean when we say these are bulk contacts. So the number of electrons here is infinite. So as many electrons as are needed here, the contact will be able to supply to the channel. So first we will be able to say that, so point number 1 is contact 1. Yes. So contact 1, and therefore at equilibrium what will happen? It will try to fill up the electrons up to the Fermi level of contact 1. So you will notice that I have not defined the Fermi level for the channel. Now this is because when we are considering the channel in a device, it usually does not, like, the channel is not considered to be okay, I shouldn't put it like that. The occupancy, the number of electrons present or the structure of the channel itself will change depending on the external conditions. Like based on the applied voltage, I can change the width of the channel, I can change the number of electrons present in the channel. So do we have examples for this? Of course we do. So if we consider a PN junction, a simple PN junction, and if we reverse bias it, what will happen is that the depletion region will grow. And in the depletion region, there are no free charge carriers. So depending on the external conditions, we can actually control what happens in this interface region, which is why the channel does not have its own defined Fermi energy. The Fermi energy is defined by the contacts. So contact number 1 will try to fill the channel. So the channel will have some energy levels in here. So like depending if it's a 1D channel, like we've seen how the energy levels vary for a 1D, 2D and a 3D system. So based on that, there will be some energy levels over here, and the density of that is given by D of E in the channel. So it will try to fill it up to EF1. So channel energy levels up to EF1. So what we are going to imagine now is, initially we had, so the initial situation is the yes, so the channel is over here and the contact is over here, and at tau, I'm going to use tau for time, tau equal to 0, the channel and contact are brought together. Okay, so this is our initial condition. Let me channel contact come together. So they are essentially touching each other at tau equal to 0. Okay, so again this is contact 1 and this is my channel. Okay, so now what will happen? Like first we have to find out how many electrons move from here to here. So this is the first thing that we have to find out. So the flux, so F here denotes the flux of electrons. So flux is defined as number of particles moving through a unit area depending on the dimension. So if it's a 1D channel, there is, the flux is literally the number of electrons that are moving. There is no per unit area. If it is a 2D channel, number of electrons moving per unit length along the width of the channel. If it is a 3D channel, number of electrons moving through the channel per unit cross-sectional area. Okay, so the units of flux will change based on the dimensionality of the channel. So please keep that in mind. However, we shall not be looking at the units of the flux, but just for the sake of clarity, I am mentioning that. Yeah, just 1 second. Yes. So now what we are going to do is we are just going to take a simple model where the movement depends on the difference in the electron, charge density. Essentially, when the charge density becomes equal, the flux will go to zero, and we are assuming that it varies linearly. So in that case, what is going to happen? We are going to have, so let us define, let me call this point as 1, because I'm going to call the contact number 2 and channel connection as point number 2. So initial, so N naught at a certain energy E, yes. So, and the filling of the energies will depend on how many electrons at the same energy are present here. So it is going to be N naught E on the contact side. So that I'm going to call, oh no, what I'm going to do is I'm going to call it N of E, because N of E is on the contact side. Okay, so yes, so N of E, so this is the contact carrier concentration minus, and let me call this N naught of E. So N naught of E is in the channel, so this quantity is in the channel. Okay, divided by, let me say tau. In fact, I will say, since this is across junction 1, I will say this is tau 1. So as the time keeps increasing, these two quantities will come closer and closer and closer, and at a certain total time, we will assume that the contact 1 is able to completely fill all the energy levels up to EF1 in the channel. Now N of E is given by D of E is given by D of E F of E. So this is, I mean, technically speaking, I should not write it like this. Let me be accurate here. So in fact, I will not call it N naught. Let me again just put the subscript C over here. Okay, so this is NC. NC denotes the charge carrier concentration in the channel. So yeah, just yes. So N of E dE, yeah, this is the correct way to write it, is equal to D of E, which is the density of states, times F of E D. So the whole thing is integrated to get the complete electron density in this case. So this is for this case. So this will give us the rate of change of, like, this will tell us what the rate at which NC is changing. Okay, so this quantity is the number of electrons that are coming into the channel, which implies, so I will call this F1. F1 will be equal to dNc of E by dt. Okay, so again, this should be F1 of E. Yes, I should clarify here. So this is the Fermi distribution function for material 1, which implies EF will be replaced by, EF will take the value EF1. So F1 is equal to dNc of E by dt. Now similarly, I can, where are we? We are over here, yes. So yeah, let me start a new thing. Yeah, so now similarly, we are going to look at contact number 2. Again, same conditions as before. At some time tau, these two things are brought together. So again, we are looking not at the, like, this is, oh, sorry, this is not the like this is not a geometric representation of the system. This is the energy diagram. So this is, now this material is going to have a Fermi level EF2. This is contact number 2. Let me just maintain some color consistency. So this is contact number 2. And now what is contact number 2 going to do? Like under a normal circumstance, the contact number 2 will try to fill up the system up to EF2. Now what does this mean? If there were electrons present at energy level above EF2, contact number 2 will take them. Contact number 2 will absorb them. So what has to be understood here is this quantity F1 can be positive or negative depending on the value of energy. Okay, if the energy is above EF, then this quantity will move backwards, because typically in any material, even at a finite temperature, the number of electrons present above the Fermi level will be very less. So F1 can be positive or negative. I'm not saying the electrons are only moving in this direction or over here. I'm not saying the electrons are only moving in this direction. No. It depends on how many electrons are present in the channel, and that is what we want to find out under particular conditions. So in this case, what is going to happen is, again, we have our energy levels over here. Again, the channel will have some density of states D of E. Remember, we have not spoken about the density of states of the channel yet. Okay. And in fact, okay, let me do that. Or rather, I will define that in a minute. Okay. So that is what is happening over here. Now again, what we can say is, now by convention, we will assume that contact 2 has a lower Fermi level. Therefore, contact 1 will supply electrons to the channel and contact 2 will remove electrons from the channel, just for the sake of convention. It can be the other way around. Both the Fermi levels can be same. Anything is possible, but for now, just for the sake of understanding, we will write it like that. Which implies NC of E, oh no, what color did I use in the previous slide? I used blue. So let me use blue here as well. Yes, so NC of E minus, and what did I call this? Let me call this N1 of E. Minus N2 of E by some tau 2 will be equal to the flux of electrons across this contact, this interface. Okay, and I know F2 is equal to, yeah, F2 is equal to D, again, yeah, like essentially dNc by d tau from this side. So this is the rate of increase by our convention, and I shouldn't have written dt here, or rather no, it shouldn't be d tau, it should be dt. I'm sorry, because tau is a constant. Like tau is essentially the time it takes to fill up. So this should be dt. Okay, and again N2 of E is given by D of E. Again, this D of E is for the bulk material. So this should be remembered. Whatever material we are defining, D of E is not a constant. So let me again, just to avoid any further ambiguities, I'm going to call this D1 of E, and this I'm going to call D channel. Where is the pointer? Oh yeah, there it is. I'm sorry, I just went blind for a second. So yeah, this is going to be D channel. So that should be understood, because the bulk material can be 3D and the channel can be 1D. I can connect it with a nanowire, or I can have a quantum dot in the middle. It can even be a 0D channel. So the density of states function depends strictly on the dimensionality of the system. So this is again D2 of E. Oh, sorry. Like D2E multiplied by F2E. Oh, once again I missed the integral expression. I tend to make this mistake. Apologies for that. So N of E dE, N2 of E dE is equal to d2 of E, not minus, oh yeah, multiplied by F2 of E dE. So we have to integrate to get the total electron concentration on the contact number 2 side. Now at equilibrium, what do we know? At equilibrium, we know the following. We know F1 plus F2 should be equal to 0. Because the rate at which the electrons are coming in should be equal to the rate at which the electrons are getting pulled out. So from that, what we will get is, we will get NC of E. Oh, no. I should directly jump to this. So what we shall find out is, let me again, or in other words, this quantity, like essentially the rate at which the charge carrier electron concentration is being increased in the channel should be equal to the rate at which the electron concentration is being decreased by, like increased in the channel by contact 1 should be equal to the rate at which it is being decreased in in the channel by contact 2. Okay, so just writing exactly these two quantities over here, what we will get is, just for reference, going back to the previous slide, it will be this one over here. So it is N1 of E minus N2 of, not N2, sorry, NC of E by tau 1 is equal to NC of E minus N2 of E by tau. Now what we can assume is, again this is another fair assumption to make, since we are talking about one device, usually the device is made as a whole. We don't make the source separately, the drain separately and the channel separately and attach them together. That does not happen. That does not happen. The devices are usually etched or grown on the same substrate. So all these contacts are created roughly at the same time. So that is a fair assumption to make, and especially when the devices are functioning, when I'm setting up voltages and stuff, I don't give voltage to the source first and then the drain. The voltage is set all across the device. In fact, it is set across the entire, not just this single device, but it is set across the entire complete device, the processor or whatever higher level device that is using these transistors or other devices as its building block. So the voltages are all set up at the same time, which implies all the contact potentials and charge carrier concentrations are initialized at the same time, which implies we can assume tau 1 is equal to tau 2. That is a fair assumption to make. Now this will give us NC of E, like essentially we can move NC of E over here and get this over here. So NC of E will be equal to N1 of E plus N2 of E divided by 2. And from this, since we use this expression and since we assumed that these are both bulk contacts, we can assume both of them to be 3D, in which case D1 of E will be D2 of E. And from that, we will get the final expression N is equal to integral D of E. Since we are assuming the source and drain are, similarly shaped materials. I'm not saying they're the same material. They are both 3D contacts. Okay. Or they are both 2D contacts. Like whatever it is, they are of the same form into F1 of E plus F2 of E by 2 times dE. So this is the charge stored expression for charge stored in the channel, and that's what we have here. Now from this we can also intuitively understand something. So what will usually happen at equilibrium in the channel, like up to what energy level will the electron be present? So that should give us the Fermi level across the device, or more importantly the Fermi level in the channel. So this can be used to understand that. So what will essentially happen is, For very high energy levels, they will get readily absorbed. But typically, when this average condition holds, we will find that the charge that is present in the device will go up to, let me just create a new slide. So, yes. So, at equilibrium, what will essentially happen is, because now there are two Fermi levels, so the contact one will always try to keep filling up electrons to energy level EF1, and the contact 2 will try to keep the level at EF2. So these two are both competing. What we have found out is the equilibrium condition where some electrons are being stored in the channel and the rest are just moving. So up to what point are these getting stored? We can see that in a straightforward fashion that it will usually be half of the electrons that are being sent in by contact 1. Assuming EF1, yes. Here we are assuming, of course, we will find out that the expression holds regardless of assumptions. But right now we are assuming EF1 is greater than EF2. We are just making this assumption to make things smoother. Okay. So what will happen is, at equilibrium, exactly up to the midpoint of these two energy levels will be filled. Anything above that will be immediately taken by the channel, taken by contact 2. Anything below that, of course, the contact will be taking, but up to that level, contact 1 will be able to supply, which implies at equilibrium, EF for the device will be EF1 plus EF2 by 2 at equilibrium. Okay. So when the net charge flowing into the channel is equal to the net charge flowing out of the channel, this is the equilibrium Fermi level. So this is called the equilibrium Fermi level. Now this will not always be a constant, like the Fermi level will not always be a constant, because we can apply voltages across this channel. So when we can apply voltages across this channel, we will have essentially cases where the Fermi level shifts. And again, we are familiar with this effect. However, we are not dealing with that right now, so I am not going to go into any further details about that. So this is the derivation for the stored charge. So this part is done. Now moving on to the current. So now again, just for the sake of completion, let me call this part A, and after this we begin part B. Now part B, we have to find what the current flowing through the channels. Now here we have to assume that equilibrium is broken. So when equilibrium is broken, and furthermore, let us assume a potential difference. So to a potential difference, or rather, why worry about it? I mean, it will become straightforward when we look at what's happening. So let us not even consider the case where an external voltage is applied. But however, invariably in all cases an external voltage will be applied. But if we are looking at cases where an external voltage is not being applied, then we can simply say the current, because current is a continuous variable, it cannot achieve discontinuities, because if there is a discontinuity in the current, it means charge is being created at some point in the middle of our channel or somewhere in the device. But that can never happen. So like, I mean, under normal circumstances, at very high energies, of course, we can create particle-antiparticle pairs, but even then charge will be conserved. So yeah, even in all cases, charge cannot show up out of nowhere. Yes, I correct my previous statement. In any case, charge is not going to appear out of everywhere. So first, I is continuous across. Oh, sorry for this bad spelling. Yeah. spelled correctly, it is, yes, across the entire device. Current cannot have any discontinuities. So in that case, what we can simply say is the current I is either QF1 or it is minus QF2. It is the rate at which charge is entering through the channel or leaving, entering into the channel or leaving from the channel. And we know F1 is N1 minus NC, like essentially F1 at E. We know this to be the case by tau. Now we have defined NC in terms of F1 and F2. So we are directly going to use that. So what we will get is, so what we will have is, so it is Q times this quantity. So therefore I will be equal to Q. Let me keep tau over here separately for a second. This is going to be N1 of E minus, now NC can be written as, NC of E can be written, was written as this quantity, N1 of E plus N2 of E by 2. So this is going to be written as N1 of E minus, sorry, plus N2 of E by 2. So this is the total, like this is the current. Essentially what I'm saying is this is the current rate of change of charge at a particular energy. So this is I of E. Okay. Again, like a D should be present here, but now just for the sake of convenience I'm dropping it. So now this will become Q over 2 tau. Again, tau will depend on E, because we are solving all of this at a particular energy level. What we are asking is essentially, if I choose a particular energy level in my channel, what is the rate at which electrons are moving in and out of that channel? That's all. Okay. So again, all energy levels need not, okay, I will come back to that at the end. So now this can be written as N1 minus N2. Should write it as N1 of E minus N2 of E. So N1 of E minus N2 of E. Okay. Now we know N1 of E and N2 of E in terms of the density of states and the Fermi levels, the Fermi functions. So to that end, what we shall do is, yeah. Oh, nice. I'm getting blank slides. Good. So, yes. So we know N1 of E is D of E. Again, I'm retaining my old assumption. F1 of E and N2 of E is D of E. Oh, is D of E, F2 of E, and from this we will get I of E is equal to Q by 2 tau. Oh. It's going to be Q over 2 tau of E into D of E into F1 of E minus F2 of E. So this is how the I of E is going to be. Now the quantum mechanical effect, we use essentially tau of E, we use this relation. We use gamma of E. Let me write gamma correctly. Yeah, so gamma of E is equal to h bar. So here it is not h, it is h bar, which is h by 2 pi by tau of E So we are going to use that relation over here, which implies I of E is equal to, now this Q is a constant, so I'm going to like keep it like I'm going to take it like separately for a second, and I'm going to write this as into, yes. So if this is the case, then this implies tau of E is h bar by gamma of E. So this is also true. So now I'm going to keep Q separately and 1 over, and I'm going to take this half factor over here. Now you can ask why I'm taking the half factor over here. It's also a constant, I can pull it out. But well, essentially in our charge integral, I have a f1 plus f2 by 2. So just to keep the whole thing symmetric, I will do an f1 minus f2 by 2 over here. So I'm going to write this as, this is h bar by gamma E. So now 1 over tau E will be gamma of E divided by h bar into d of E into f1 of E minus f2 of E divided by 2. Now this is h by 2 pi, so finally the 2 pi will essentially like 2 pi will move to the numerator. So what I'm going to do is I'm going to keep the pi inside and I'm going to take the h outside. Now you can ask why I'm doing such weird separations. The answer will become apparent in the next week. So right now it might seem like a rather arbitrary thing to do, but bear with me, there is a reason for doing this. Into pi into dE, and sometimes people just write it as d by 2. So into f1 of E minus f2 of E, and now I can write the total current as integral of this quantity dE. So this is the current expression, and this is essentially what was written way up here. So gamma of E pi of E dE by 2 f1 of E minus f2 of E by 2, and 2q by h is the quantity here. You can ask why 2q by h is so important. Once we go into the mode derivation, the deal about this will become important. Now let me briefly talk about what modes are. So essentially what happens is, now gamma of E is the energy broadening. So this is the energy broadening. Okay, now what does this imply? An electron moving through the channel, let us say an electron, like, so what, okay, so before even moving through the channel, I should, yes, let me rather mention it like this. So what happens in a ballistic channel? So what happens in a ballistic channel is exactly this. I have my contact number 1, then I have my channel, and then we have contact number 2. I'm drawing them separately for a reason here. Okay, so in nanoscale devices, this should be understood very well. What essentially happens is, there is an energy level E over here. So electron transport is not the physical movement of the electron. What essentially happens is, an electron migrates. Okay, so let me draw another energy level here. Now this entire line just denotes it's an energy level in the channel. Okay, I'm not saying this energy level is over space. So that is the point. This is kind of a muddled diagram, but kindly bear with me. Okay, so and there is another energy level over here. So what happens is an electron essentially transitions from this energy level to this energy level, and then after a certain time it will transition from this energy level to this energy level. So this is what we mean by charge conduction in a ballistic channel. Ballistic charge conduction is not actual translation of the electron. The transport of the electron is fundamentally quantum mechanical. However, for reasonable channel lengths, so this process, this is fundamentally quantum mechanical. So this is not something that I can describe classically. I cannot say there is a point electron and it takes a new energy value and it moves for a certain time. No, none of that can be mentioned. However, as an approximation, I can assume that this process is equivalent. Now, this entire process is equivalent to this scenario where we have, so now I hope you understand why E becomes an important thing. Now E is all important because it depends on the energy level available here, the energy level present here, and this is E1, this is E2, and this is EC. Typically this is what happens. E1 is greater than EC, which is greater than E2. So moving from E1 to E2, it loses energy. Moving from E1 to EC, it loses energy. Moving from EC to E2, it loses energy. Okay. Now, that is what is happening. Quantum mechanically, that is the process. The electron loses energy twice when moving from contact 1 to contact 2. However, we can assume this to be an equivalent classical process where I have an electron that moves ballistically through the channel. Ballistic means it is just moving on its momentum. No external driving force is present and it is just taking a trajectory with whatever initial impact was given to it. Okay, so this now I can assume as a continuous transport. So this is ballistic transport with one important assumption. Remember, some energy is lost from here to here and some energy is lost from here to here. So this is ballistic transport with energy loss occurring. So I have a delta E over here and another kind of delta E occurring over here, occurring at the channel contact interface. I can equivalently analyze it like this, and more or less I will be able to understand what is, or rather we will be able to understand what is happening in such a device. So this is important, and this is why I wanted to do this complete derivation so that we understand what is happening here. And of course, related to this, there are questions. So if you go through this, you should be able to answer those questions. So energy loss does not occur anywhere in the channel because movement is ballistic, no collisions, no energy transfer is happening between the electrons. It is just losing some energy in entering the channel and it is losing or gaining, like some energy transfer happens while entering the channel and while leaving the channel. Usually it's an energy loss. So energy loss happens moving from contact 1 to the channel and then from channel to contact 2. So these are the only two places where energy transfer happens. Unlike classical theory of conduction where energy transfer happens for every duration of the relaxation time. Like it travels without any collisions for relaxation time, also called tau, unfortunately, and then it undergoes collision, so some energy is transferred. It undergoes some scattering. Okay, so here that does not happen. So this quantum mechanical thing is equivalently replaced by the ballistic transport model. So this 3 line is the equivalent side. Like usually it's done horizontally, but since I'm equating two things vertically and just drawing it vertically. So this is equivalent sign. Okay. So now what does energy broadening signify? It just signifies this. When this process happens, now this takes a time tau. Okay. So this process, let me use a different color again. Yes. So this takes time tau. So this is where our transit time comes from. Transit time is not the time it takes to move in reality. In reality, what happens is it occupies this energy level, and after a certain time it occupies a new energy level. That is all. Like, we cannot understand the motion because it is quantum mechanical. We cannot follow the motion. Again, that is due to the Heisenberg uncertainty principle. Like, of course, the electron moves from here to there, but we cannot say in what direction it is moving or what velocity it has. But we can equivalently treat this as a particle where it moves with constant velocity across the channel length L. Okay. And what is the condition? The energy now will vary, and that variation is the energy broadening. Because it spends a finite amount of time in the channel, the energy will no longer be exactly E. It will fluctuate about E, and the fluctuation, or rather to be more precise, the standard deviation of the fluctuations is given by gamma of E. Okay, so that is what we mean by energy broadening. So an electron, a ballistic electron that is present in the channel no longer has a unique energy level. It has a small band of energy levels. So of all the energy levels in the channel that are participating in conduction, only some of them, of course, like depending on the value of EF1 and EF2, only some of them will be able to move electrons from contact 1 to contact 2. Now, each of them do not have a precise energy level. They have a slight, broadened energy levels because the electron spends a finite amount of time in the channel. And that broadened energy levels in the channel. So, the broadened energy levels in the channel are called the modes. Okay. So those define the modes. Okay. So when we are talking about modes, essentially what happens is there is a certain range of energies that the electron can have to move through the channel from contact 1 to contact 2. So depending on the availability of these modes, conduction may or may not take place. So this is equivalent to this phenomenon. I cannot say it is equivalent. It is somewhat similar to what we observe in field effect transistors. Essentially, we say that a channel exists, and when we apply the saturation voltage, we say a pinch off happens and things like that. So those phenomena explained at a mesoscopic level, at the nanoscale level, get replaced by these quantities. Essentially, we get modes, and we will have the availability of modes. So those things will start in the next week. So mode calculations will be done then, and then of course you will understand how the resistance of the channel, how to define resistance in such a device, because of course there is going to be a resistance because energy loss has happened. So since energy loss has happened, that can be replaced by an equivalent resistance. So what we will do is this delta E here will now be forgotten, and this will be moving through a channel with a constant resistance. So how to define that? That's of course the next week of the course. So we shall do that only then. And so these are called modes. Further details we are not doing, we shall start the next week. So finally, coming to the last problem of today's discussion. So now what we have been given is an electron is traveling through a ballistic channel, and it undergoes energy broadening of 0.01 electron volts. Now estimate the, let me be more precise here. We need to estimate what is the ballistic velocity. Okay, not the actual velocity, because actual velocity cannot be known. It's again uncertainty principle. Now, if I equivalently treat this as, oh, okay, I've mentioned ballistic, so I'll also mention it here. So the ballistic velocity of the electron, if the channel length is given to be 20 nanometers. So how do we find this? So to find this, what we have to do is essentially, first, we have been given gamma of E. So gamma of E is given. Now gamma of E is equal to 0.01 electron volts, which implies tau of E, which is the time the electron spends in the channel, okay, is given by h bar by gamma E. So if we like essentially h bar is again, if you plug in the constant values, h bar will be how much? It will be 1. I think 09. Yeah, something like that. 1.09 into 10 to the power minus 34. Again, not very sure about this. 1 point something. Wait, how much is 6.6 divided by 3.2? Oh yeah, it's 1.09. It's approximately 1.1. Yes. So joule second. So that is the unit. And 1 electron volt is 1.609 into 10 to the power minus 19 joules. So again, this is to show that the dimensions match. So this is joule second, this is joule. So dividing this by this will give me some unit in seconds. Now this is 0.01 electron volts. So that will give us tau of E to be equal to 6.58 into 10 to the power minus 14 seconds. So the amount of time that it is spending in the channel is very, very less. So it is just spending 10 to the power minus 14 seconds. So that is like actually even less than picoseconds. It is almost at the level of a femtosecond. So this is very small. So it's quickly transitioning. Of course, I'm not saying this is how it typically happens. For this problem, this is what is happening. Okay. So usually the energy broadening is actually not this high. It is even smaller than this, but just for an example, I'm giving this as a value. So in this case, it will spend these many seconds in the channel. So now how we can estimate the velocity is, the length is 20 nanometers. So V ballistic at this energy E is length of the channel divided by tau of E. So that is 20 into 10 to the power minus 9 divided by 6.58 into 10 to the power minus 14. So this will give us a velocity of 3.04 into 10 to the power minus 5, not 10 to the power minus 5, 10 to the power plus 5. Yes, and this is important. This is why this particular numerical is being done. Meters per second, or it is 3.04 into 10 to the power 7 centimeter per second. Meter per second or centimeter per second. Now, for people who are familiar with classical models of conduction, you know that the drift velocity of an electron is usually micrometers per second. So it is like, I will write that here. So classical drift velocity is to the order of micrometers, or rather let me write it in numbers, is of the order 10 to the power minus 6 meters per second. So you can see that the effective velocities that we are getting for the electrons in ballistic transport are enormously high. Like it is, I mean, even if we compare it to this, it's 10 to the power 13 times. It's like 13 orders of magnitude. Oh, no. It's 10 to the power 8 over here. So it is actually 8 and 7. It is 15 orders of magnitude larger than the classical drift velocities. But we should remember that this perceived high velocity is over only 20 nanometers. It is a very small length. Like this drift velocity is for conductors that are meters, even kilometers long. So in that case, this drift velocity is a valid value, but these high velocities, it's not like the electron is traveling with this velocity throughout like the complete extent of what to say, like, or rather through macroscopic scales. No, it is having this velocity, or rather it is, we can treat the electron as having this ballistic velocity only if the channel length is this small. Now what happens if the channel length increases? How will the ballistic velocity change? Again, this will be done as we move further and further. I think either week 5 or week 6 will cover this part. So just as a prelude to what is happening, this particular numerical gives us a flavor of how high the ballistic velocities are, provided the energy broadening is in this case. You can try out the same problem with different energy broadening values. In fact, you can even figure out the energy broadening for which we get classical drift velocities, and people who are inquisitive can try to guess what those energy values correspond to, like what do they mean. I can tell you that typically having energies less than 10 to the power minus 34 are not meaningful. So that is a clue I am willing to give you. Not even 10 to the power minus 34, even like 10 to the power minus 20 joules is, no, not 20. 10 to the power minus 30 joules is like too small. Okay, so you can see what happens. So this particular problem is, it is not for any assignment. This is to give a flavor of what is happening. This is to understand the physical phenomena, or rather the way in which we treat the physical phenomena in nanoscale devices. And with that, we come to the end of this week's session. This week it's a relatively shorter session due to the fact that not many numericals were being done today. So I thank you. I thank the attendees for attending live, and again, thanks to everybody else for listening to today's session. I will meet you all again next week, same time. So that is all.